Rohit, can you hear me now?
Yeah, yeah, yeah. You are audible.
Okay. Yeah, so now I can hear you well as well. I don't know what was the issue.
Yes, sir.
Yeah. How are you doing? You okay?
Yeah, I'm fine, sir.
That's good. That's good.
How's everything
So I
there?
think,
Yeah.
yeah, so everything is good. Yeah, just traveling a little. So if okay with you, maybe I can start to share my screen and just present since
Yes,
we are
sir. Yes.
already late.
Before that, I would like to introduce you with your permission, sir.
Yeah, yeah, please go ahead. Yeah.
Yeah.
Thank you.
So first of all, I would like to thank you for accepting my invitation, and let me introduce to you participants. We have with us Dr. Aryan Kaushik. He is an assistant professor at University of Sussex, UK, and his other research and visiting professor appointments also include uh, he is also connected to Imperial and has been connected to Imperial College London, University of Bologna, Italy, University of Luxembourg, Athena Research and Innovation Center, Greece. Coming to his academics, he has been a research fellow at University College London. He has been PhD from University of Edinburgh, UK. MSc from MSc in telecommunication from Hong Kong University of Science and Technology. Coming to his roles, so they are what I can say. So he has been contributed a lot and is being contributing a lot. So he is an editor and in IEEE communication letters, several special issues he is handling. So he has been in many teams also he has delivered more than 50 keynote lectures in reputed conferences. He always associated to some of the flagship conferences, including WCNC, ICC, Globecom, PMI, PIM, RC, and the names are many. I cannot include all the names in a couple of minute introduction. Coming to his publication and research domain, he has published several reputed papers, including Transactions magazines, and his research domain includes terrestrial and non-terrestrial communication, intelligent reflecting surfaces, holographic MIMO, and integrated sensing and communications. So also he is actively involved in some podcast, discussion, dissemination activities, and continuously connected to the all such ComSoc universe activities. So again, I welcome you, sir. On behalf of everyone, we welcome you here, sir. Thank you very much, sir.
Thank you so much, Rohit. Thanks a lot for the invitation. Thank you so much.
Thank you, sir. The stage is all yours, sir.
Yeah, thank you. So let me just try to share my screen, if okay. So 1 second, we have. So are you able to see my screen? Is that okay?
Yeah, yes, they are visible.
Okay, so let me try to just open these. Okay, so
slides are visible, sir. Before you start, can we request you to record your session if you allow so?
Yeah, please go ahead. Yeah.
Okay.
So you can record
Thank you very
from
much.
your side, right? Yeah, no
Yes.
problem. Okay, so should I start, Rohit?
Yes, sir. Please go ahead.
Thank you. So thanks everyone for attending my session, and thank you, Rohit, for such a nice introduction. I really appreciate your invitation. So today, I think my talk is based around integrated and intelligent wireless connectivity. So basically discussing sort of roadmap to 6G and how we have been overpowering our previous sort of standards, 4G, 5G, and so on. And I'm based at the University of Sussex, as Rohit mentioned. And I've also given a link to my email and website, so please feel free to approach for discussions or any queries or any sort of collaborations. I'm always open for that. So just a bit of intro. So I'm associated with Sussex, as I mentioned. Before that, I was with UCL, Edinburgh, and I had done my master's in Hong Kong, USD as well. I've led some projects very recently on the topics that Rohit also mentioned, basically on NTNs and ISAC and so on. Fortunately, I've also been associated as visiting professor and a researcher as well with a couple of institutes. I've been a panel member very recently for UK PSRC ICT funding proposal panel as well, and I've been reviewing some proposals as well. So those of you who may be listening from the UK may be aware of this organization. I'm also associated with 160 as well, which is another consortium that has been working on 60 technologies and sort of dissemination activities as well. Before that, I was also PhD thesis examiner at UC3M. So last year it was that I had been an examiner in that committee for one of the theses. And I've also led several roles as editor in different journals, guest editor as well. I've also delivered several tutorials and invited speeches in many venues. I've been also a chair in different organizing and TPCs, organizing committees and TPCs as well, namely ICC, WCNC, and a couple of others. I'm also quite active in organizing workshops with ComSox. I'm an active member there. Have been organizing workshops with different colleagues in many of the events and conferences and so on. Also, we have some upcoming books as well. So one of these is on ISAC, which is Integrated Sensing and Communications. One of that will be at the end of year, or hopefully next year, would be on non-terrestrial networks. And another book that we are in process is with electromagnetic signal and information theory. So I'm editing these 3 books as well for publication. So just going into the technical aspects of the talk. So what have we been expecting really from our 5G and 5G advanced sort of services? So as we see that 5G subscriptions are basically estimated to reach about 5.3 billion by 2029. So if you look at the industry reports, so namely Ericsson Mobility Report, if you check one of their latest versions, so they expect that 5G subscriptions are going to just get high in number, right? So 4G is not going to be so present in next couple of years as 5G would be, right? So there wouldn't be much change into 4G services already, but 5G subscriptions are supposed to cross a 5 billion mark by end of 2029. And by the same year, we also expect, as a case study, in Western Europe to have about 560 million subscriptions for 5G already, and there have been several worldwide efforts going on for 2030 and beyond as well. So we expect that our 5G services, which we are already, kind of initiated a couple of years ago, have been ongoing in several sort of geographical locations as well. We are expecting them to just grow over the next couple of years and have most of mobile connectivity based on 5G subscriptions. At the same time, in parallel, we have been working on 6G as research and industry sort of community. However, we expect that 5G coverage would be quite high by next couple of years. And still, this is at a very initial sort of stages in last couple of years, but still it needs to reach its mature point, which it has not achieved yet, because the promises that were done for 5G are still sort of pending. Most of the promises are not fulfilled. So this is what we are expecting with our 5G and 5G advanced sort of services in the next couple of years. And I would like to mention that there are different sort of use cases or user scenarios, as we call it, that we had considered in 5G, basically. So one of them was, so anyone who is working in this communication area must be already aware of this, but just to kind of recall. So one of these is ultra reliable low latency communication. So basically to make our communication sort of as reliable as possible, especially when we are dealing with, let's say, sort of non-terrestrial entities, to make low latency or low delay based communication. Massive machine type communication is basically to have deeper networks, massive connectivity as well. One example could be, let's say, V2X sort of scenarios. So we really want like sort of massive connectivity based on our infrastructure, right? Another one was enhanced mobile broadband. So always since 3G, 4G, we have been aiming towards very high data rates, high speeds, and to have high and high, capacity of our services, right? So these has been some usage scenarios that we considered when we expected 5G, or so to say IMT 2020 standard. But then in 5G Advanced, which we expect in the next couple of years, is basically to just work on these user scenarios already, right? So we do not want to change the whole infrastructure, but gradually we want to shift from providing these sort of services, these user scenarios, considering these user scenarios, to kind of expand on the current infrastructure. So that's why there is a plus that you see here, basically, when you talk about sort of 5G Advanced. And in parallel, we work on next generation systems and networks as well. So coming to 6G, so basically we do see that there is quite number of efforts going on 5G Advanced side, but at the same time, the research and industry community is quite active in making IMT 2030 or slash 6G as one of the realities as well, right? So if you follow the recent sort of news and the updates, so basically we have seen the ITUR sort of adopted framework, so 6G framework. So we have moved from 3 usage scenarios of EMBB, MMTC, and URLLC, as I mentioned earlier, to 6 other sort of user scenarios with enhanced capabilities. So basically, first one is, let's say, integrating sensing and communications. So basically, if you were having your services, let's say for sensing applications, you were implementing them, let's say 3 gigahertz or 4 gigahertz, and at different frequency, you were implementing your communication sort of applications. So basically, you can actually combine them under one network. So either it can be a coexisting network, or it can be sharing a similar hardware as well, where you can use these as dual function signals, where some component of this is acting as a sensing signal, some component of this is acting as a communication signal. So different choices. At the same time, we would like to save the hardware and spectral resources as well. So that was the idea, that you want to combine different operations together. Similar concept is with AI and communication as well. So basically, we have been seeing since many years that how AI, can do like a paradigm shift for communication. But at the same time, we need to sort of understand how communication can be useful for AI applications as well. So they have to go hand in hand as well, together for providing sort of advanced multifunctional services when it comes to 6G. Then we would also like to have a key user scenario of immersive communication. So basically, your extended reality or any sort of virtual reality sort of scenarios could come under this. So basically, you want to have more and more immersive based services and applications as well. And at the same time, you want to keep ultra reliability or hyper reliability, as they call it in the next standard, and low latency as well. You would like to keep. You want to have ubiquitous connectivity. So basically, you want anytime, anywhere, anything sort of connectivity. We will discuss this in later half of my talk, how we can enable ubiquitous connectivity as well through the current infrastructure that we have, and what kind of additions that can be done there. And at the same time, we want to keep our massive communication goal as well. So basically have deeper connectivity, massive connectivity among different entities as well, among several entities of communication entities. We would like to keep that as well. With all these 6 key usage scenarios, we would like to keep our objectives of sustainability, connecting the unconnected, or having our systems, our networks secure, private, resilient as well, and make them ubiquitous as well, but at the same time make them intelligent, or dynamic or adaptable to the changes in scenarios. So all these discussions have been taken into account when deciding on the 6G sort of framework. So key takeaways are multifunctional, massive connectivity, immersive communication, has to be AI and then comms together, ubiquitous connectivity, reliable, sustainable, resilient, has to be secure, private, sort of have to work on the privacy issues as well, especially in the cases of, let's say, non-terrestrial networks, it becomes quite important, or some other scenarios as well. So as you can see also that these are basically the enhanced capabilities and enhanced usage scenarios that we're considering for 6G. Recently, 6G logo has been also approved, which I've shown here from 3GPP. And then there has been some, special mention that I would like to say here is from the UK side. There's an effort going on again through a project Gigabit from the government. So basically, there is the broadband rollout by Building Digital UK, which are expecting 85% of the UK to have access to gigabit capable speeds by 2025. So this is what our expectancy is, especially in this case study of UK efforts, right? And if you would like to have some more look about about this evolution towards 6G, so Rohit has led a paper very recently with myself and many other collaborators who work with us, discussing several scenarios, several sort of enhancements and challenges that we face, several trends as well. So you're welcome to have a look at this paper as well, based around this discussion. This is also one thing is in the same paper which Rohit has led. So basically, we have discussed the all the aspects. So where we actually started from our early sort of standards and where we are actually at the moment. So basically, we have started already with release 19. So release 18 has been going on until very recently. Release 19 early sort of study items and system aspects have been decided as well in December 2023, right? So if you would like to have a look at what are the sort of overarching aspects as well of IMT 2030 and how the trajectory has been since we started our standardization, you can have a look at this paper as well, right? So basically, the idea here is that from 5G to 5G Advanced, we have moved to several other key usage scenarios, as I mentioned in the previous slide as well. So different ways to sort of say these for 6G, right? So in terms of standardization as well, so this is what we have been talking about in terms of framework and how 6G should look like. So what are the efforts actually going on for 3GPP releases as well? So release 18 basically has been working on sort of enhanced RF requirements for different frequency ranges. So this is also quite important because our spectrum is quite limited. So we would like to make use of our spectrum in a more intelligent manner, but we need to check that whether which spectrum is really useful for our applications. So let's say we were during 5G Advanced, we were moving towards millimeter wave spectrum as well, sort of high frequencies, and keeping, the current infrastructure as well, keeping that in mind. So we wanted to still utilize our microwave spectrum or our sub 6 gigahertz frequencies as well. And there has been a lot of research in recent period on sub-terahertz and terahertz as well. But with 6G, we will discuss in the next couple of slides what we are really expecting with our sort of spectrum sort of usage. I mean, what we are really expecting through that. So I'll discuss that in next few slides. But concerning with 3GPP, so basically there has been different RAN groups as well. So they look at different aspects of these technologies, right, to make it ubiquitous sort of connectivity, immersive communication, AI-based services, or any other, computing sort of solutions, edge computing, cloud computing sort of solutions, network enhancement or making it energy efficient, increasing the capacity. So there have been different sort of objectives in different RAN groups as well. But these quite align very well with the objectives of 6G as well, what we are really expecting our 6G services to do. So we need to standardize these as well, right? So 3GPP has been working on these on these aspects. And release 19, so basically there have been key points. So they are exploring massive MIMO, high mobility scenarios, again AI or machine learning, and their applications to next generation RAN, extended reality, energy efficient solutions. NTN is also a part of that has been since release 17. So NTN is also a very important aspect, especially LEO satellites or high altitude platforms in the air. So these are quite useful, let's say, when it comes to standardization. So the efforts have been going on. Then also very recently, there have been works on sensing communications core design. So very initial sort of system aspects or very initial study items, but that has been aimed in release 19 to study the core design of sensing and communication. So basically communication assisted sensing or sensing assisted communication. These are the two scenarios that will be focused upon at the early stage. And there have been 32 industry use cases as well that have been considered for functionality requirements in this context of sensing and communications. Several efforts have been going on. So let's say 802.11 BFWLAN sensing as well from IEEE that has been standardized. 160 is working quite a lot on different, next generation MIMO or several other sort of technology groups as well, let's say 6G empowered robotics and many other sort of working groups they have. X as well is one of the European flagship projects. They've been working on making AI and machine learning based sort of applications and services, sensing and communications as well, and many different topics they've been working on. They've been really leading the effort. Then 5G Alliance for Connected Industries and Automation as well. You can see some white papers from this group as well, where they discuss the latest trends and technologies and so on. So really, with all, in terms of the standardization, in terms of the objectives that we have set, the targets that we have set, it seems that these are achievable. And it seems that the efforts are going on in various working groups worldwide and many sort of service providers or researchers, they have been working on different sort of technology aspects related to this. Then in terms of the spectrum, so as I was mentioning, so I wanted to touch this slide as well, that in 6G that we have considered is centimeter wave will be considered as an essential spectrum, right, as an enabling spectrum for 6G services. So basically it goes in the range from 7 to 15 gigahertz. So they say that about 7 to 8 gigahertz is a good sort of band to increase the capacity and coverage. Already you can find different applications, about 8 gigahertz, let's say, radars are being used for different applications like weather monitoring, air traffic control, maritime security, and so on. Then we also consider that if we go quite close to, let's say, 14, 15 gigahertz, that may not be the best idea because that will have the characteristics quite close to millimeter wave. Even though in previous years there have been mobile service providers using at least some unlicensed spectrum or licensed spectrum for through using millimeter wave for their services, but still it has not really overgrown as we were expecting. But still there have been different sort of user scenarios that have been considered at millimeter wave as well. But concerning with 6G, we are considering that centimeter wave will be an enabling spectrum, and very high frequencies, let's say sub-terahertz frequencies, 90 gigahertz and beyond, will be considered as complementary spectrum. So you may not require it at each and every geographical location, but wherever you require them, that could be like a complementary spectrum for those services. And it becomes more important than ever, is basically whether our current objectives or current technologies that we are considering to be implemented in 6G, are they really deployable? Are they really useful at such frequencies? So let's say if you consider centimeter wave, as I mentioned, X band, so about 8 gigahertz is being considered for, let's say, sensing radars and so on. 77 gigahertz or about 80 gigahertz is considered for automotive radars as well. So we do see some existing applications, but we need to still keep in mind that when we are talking about using new technologies, are they really deployable at such spectrums as well, right? Again, you can gain very high sort of terabits per second sort of speeds and so on by using massive MIMO or very high sort of high degrees of freedom for your antennas. But still we need to keep in mind that how useful new technologies and advanced technologies would be going forward to these spectrum bands. And terahertz has always been, in last couple of years, has been, attracting quite a lot of attention as well. So going to very high frequencies has its own sort of drawbacks as well, as you may be all aware. So you have very high, let's say, blockage effects or very high, propagation losses. Long line of sight of communication can be a bit tricky as well at high frequencies, but still the advantages are there as well. So it has been really explored in different theoretical works or different experimental observations as well. So in the paper that we did with Rohit as well, so we mentioned about the efforts from our colleagues from NTT who have been working on some sort of multiplexing approaches, some angular momentum multiplexing approaches for terahertz frequencies. So there have been some efforts going on terahertz. You can find many papers as well on the technology. So we have not really just scrapped this technology completely, but we expect that even beyond 6G, we expect this technology to be explored more and find more answers to our questions that we have currently. So just going a bit further is basically, so I talked about the 6G framework and what are the key sort of user scenarios it has. So one of those key user scenarios and one of the updates that we have here is basically using sensing and communications, right? So to integrate sensing and communications together, right? So as I was mentioning, whether to coexist these in a single network, to save on your spectral resources, to basically use the same frequencies, or to actually have them on the same hardware as well. That is also possible. So you have a dual function signal. Some components of these are corresponding to your sensing part, and some of these are corresponding to your communication signal as well. So different ways, coexistence or joint system, but the main idea is to actually integrate these two operations together to really make your system or network multifunctional, right? And we have also discussed some, sort of standardization activities that have been going on, some pre-standard activities that have been going on, let's say from ETSI or some other sort of industry activities that have been going on, and what are the latest challenges or trends that have been been considered in recent times. So we have one accepted paper very recently. Again, Rohit is also a part there. So if you would like to go through this paper, please feel free to go through that. And we have also given sort of a blog post on the technology as well, how it is important for the evolution of next generation networks with our colleagues. So one aspect here that we can consider is, okay, we do the dual function sort of signaling or sort of sensing and communication coexistence in one network, but this already gives us some advantage in terms of making it energy efficient, in terms of that we are trying to use the same hardware for two operations, and we're trying to save the frequency as well. But again, can we make it even more energy efficient? So again, there are different directions that you can think of when you want to integrate sensing and communication. So one of these that we had considered in one of our recent papers was to basically, on the system level, so when you have your quantizers and RF chains and so on, so can you actually optimize these operations, these functions? So basically, you consider a dual function signal, but at the same time, you would like to optimize your sort of hardware units as well. So let's say you want to select only a few of the maximum available, let's say, RF chain that you have with you in your hand. So you want to implement some sort of selection procedure, basically working on a fractional programming method. So you have your energy efficiency, which is dependent on your mutual information or your rate. In the denominator, you have your power consumption. So you want to maximize the rate, but at the same time, you want to reduce the power consumption as well. So can you implement some approach where you can select these, let's say, blocks that you have in your system as less as possible for the best performance possible for a dual function sensing and comms signaling. So that is possible. So if you want to implement, let's say, even hybrid beamforming here, you want to have a combination of digital beamforming and analog beamforming, and you want to really optimize your, let's say, number of RF chains or quantization units, you can actually do that. So we showed this in one of these papers, and we try to actually compare the performance as well. So it is very important when we talk about sensing and communication together, the operations together, is that what kind of trade-off they have. So as you can see here in this plot, so let's say in energy efficiency one, so if you have, let's say, fully communication performance, right? Fully communication sort of system that you have. So you have very good communication performance, which is your energy efficiency. But as soon as the sensing or the radar sensing comes into existence, you see the performance starts degrading, right? Is in many scenarios is still better than the conventional approach, because in conventional digital sort of beamforming approach, you are making use of all the available resources you have. You're not really optimizing anything. But if you are really optimizing your, let's say, RF chains or quantization units and so on, so basically here you have very good energy efficiency, but because when sensing starts to come into existence, starts to have some sort of dominance level, you see that the communication performance starts decreasing. It's the same thing when you want to compare, let's say, for a rate as well, for spectral efficiency as well, that you are quite close to the best possible case of your conventional digital beamforming, but at the same time, if your radar sensing comes into existence, it starts decreasing, the performance starts degrading. And at the same time, if you like to plot, let's say, any sensing-oriented metric as well. So in this case, we had implemented the beam pattern. So again, you can see that when you increase the weightage of radar, so the green guy here, the green signal, you can see that it performs quite close to the ideal beam pattern case. So again, it says that the higher the dominance of your radar sensing operation, the better radar sensing performance you get. Compared to when communication operation is in dominance. So this is quite important to remember, whichever problem we follow, that there has to be some sort of trade-off as well between sensing and communication operations. Then we can design it to be energy efficient, but can we also consider some other scenarios where we make it spectrally efficient? Plus, can we consider some sort of interference between these two operations? So this is what we try to do this in this particular paper, where we do consider some sort of interference in these two between these two operations. So let's say if you have your mutual information of your communication part, you have some interference, let's say in terms of the variance here. So very simple case, but is to sort of show the proof of concept. So basically, you have interference from your sensing, radar sensing part, and same thing is that if you are considering your radar sensing operation, you have interference from your communication part, right? And again, you try to give some weightage. So rho is basically here showing the weightage as well, that when is your radar sensing into dominance and when is your communication operation is in dominance. So this is, again, quite important that you can tune in different rho values or different weighting factor values, whether your sensing is in dominance or whether your communication operation is in dominance, and you can try to observe different sort of analysis as well based on that. And again, simple problem, you can use it fractional programming approach to change your sort of difference based to change it to difference based optimizations and so on, iterative parametric sort of operations approaches. So basically, the idea here is that, again, no matter what problem you consider, joint sort of for the joint system, you have to consider some sort of trade-off as well between these two operations. And again, you can consider different scenarios. You can also consider the interference between both these operations, which is quite a new direction to be explored for this topic, which we do not see quite a lot in literature, in recent literature. And then there can be some use cases as well, basically. So one of these is, let's say, if you talk about 6G empowered IoT and robotics, so ISAC can play a good role there. So basically, if you would like to have a simultaneous sort of imaging, mapping, and localization, very high level of localization, basically 3D localization, it is possible through the use of ISAC and its applications. You can have high accuracy as well for localization and tracking. You can, use ISAC functions in augmented human sense. So basically, when you're trying to do remote surgery, or you want to, detect any faults, or you want to also, work for smart healthcare, so gesture recognition or emotion recognition or fault detection, or many other sort of applications that we can think of when we talk about ISAC use cases. Again, if you're more interested into this direction of ISAC, again, I've given a link to a paper. Basically, we discuss about all these, use cases as well, and some other, enabling techniques for ISAC. So how ISAC can actually interplay with with different technologies that we're considering for our future systems and networks. So please feel free to go through that paper as well. So, in addition to ISAC, this is also quite important that, okay, we achieve multifunctional systems and networks, but at the same time, it becomes quite important is that can we also advance our system in terms of make them more smart, right? More sort of smart radio environment, right? So in this context, there is one concept that is quite catching up now is electromagnetic signal information theory. So basically, you try to work out your electromagnetic wave theory. You try to intertwine this with statistical signal processing, statistical information theory and signal processing as well, right? It can be statistical signal processing as well, but the idea is that to combine these three fields together. So basically, you want to have, let's say, your Maxwell equations from your EM vector fields and so on. You want to throw in some sort of probabilistic models as well to deal with these expressions, to solve them more easily, right? And you can also use some sort of optimization, compressive sensing, or signal processing approaches to solve these problems. So the idea is to really combine different domains together, and this is still at a very early stage, so we do not really know about the exact terminologies, but we are expecting that to make it a bit more wider term, we would like to consider electromagnetic information theory with signal processing, so we will call it electromagnetic signal and information theory. And there have been many examples that have been existing and have been going on in the last few years in terms of research. So any sort of new antenna designs or your hybrid beamforming, they can be part of these. Any sort of spherical wave modeling that you talk about, any sort of channel modeling that you talk about, any continuous aperture, so the case of, let's say, holographic MIMO, or continuous aperture MIMO, or sort of active reconfigurable intelligence surfaces. Different scenarios of, if you want to move to more indoor communication as well. Let's say if you want to move from far field to near field, you want to basically reduce your complexity, increase your high degrees of sort of freedom for your antenna selection and so on. So different sort of terms that can come under this wider sort of umbrella term. Again, recently, our colleagues have worked on this topic, and I would like to mention their papers as well, basically discussing about this concept and different mathematical expressions and so on. So if you would like to understand a bit more about this technology itself and how it is shaping in its initial days, please feel free to go through these. In the context of ESIT, so we consider another term, again, very popular term. So many researchers have picked this up, which is called reconfigurable intelligence surfaces. So basically, you have sort of a microcontroller units to operate for a large surface. So basically, the idea is to actually reflect your signal. So you transmit your signal, and you would like to reflect it in a intended direction of users. Right, and microcontroller unit is basically the brain of it behind this. So basically, how you want to reflect the signal, and again, it depends on the metamaterial properties and so on, whether it's a really like absorbing material or quite reflective material and so on. But the idea is that for high frequency scenarios, or very useful there because there are blockage effects and propagation losses, path losses quite high and so on, especially millimeter wave or sub-terahertz scenarios, or where you consider known line of sight of communication, where you have a weak non-line of sight link, you may achieve basically this reflection basically. So you have these as buffer units, so you keep reflecting your signal towards your intended direction of your user. Again, we also do some podcasts as well. So we have talked about these technologies in our podcast. There are some papers as well I've mentioned. So please feel free to flick through these papers or these podcasts. So I had hosted Marco Renzo, is a colleague who works with me in different directions of these 60 topics. So we had also met and we had recorded this podcast. So basically about intelligent surfaces, intelligent meta surfaces, the complexities and so on. So if you'd like to follow through that. Recently we had also done with another colleague colleague of ours, David Dadari. So we talk about different variants of actually intelligent metasurfaces. So metaprism is a new term. It's based on, let's say, the frequency or OFDM signaling, and it is also reconfigurable, but depends on different sort of principles. Smart skin as well, we discussed about, which is basically non-reconfigurable. So you basically just install it as you have programmed it. So this has been also discussed in our recent podcast. So please feel free to go through this if you have interest in this technology further. And one more thing I wanted to mention here was that there are different sort of variants that we talk about, definitely. But one of the basics difference that we can consider is passive or active. So basically these elements, so what they are doing is that they are just reflecting your signal and they are not doing anything else, right? So with these sort of small unit cells, you can decide to use it efficiently, but still they are not really amplifying any signal or anything. They are passive in nature, so you don't really require any additional circuitry. While on the other hand, if you want to make it active, you use some sort of reflection type amplifier in your unit or some sort of RF chains, for the beam steering. So basically, you want to actually, when you're transmitting, when you're reflecting, you want to amplify the signal as well. So that is the term that is coming under active RIS or active RIS. And if you would not like to just stick to one of these methods, you can use your different unit cells based on either active principle or passive principle as well. So you can keep your unit cell as a passive sort of beamformer, or you can use it as active beamformer as well, or active metasurface, right? So you can have different sort of elements as active or passive. There can be another new variant. So stacked intelligent metasurface is another term that has come up. Is basically to put all these metasurfaces in different stacks to enhance the spectral efficiency and so on. Simultaneous transmission reception using the RIS, holographic MIMO is going on, so it has applications in holographic ISEC as well, and so on. Metaprism, smart skin, as I mentioned very briefly. So these are some of the new variants as well that have been going on. Talking when we talk about risk. And again, I mean, we can consider some sort of case studies in this. So one of these is basically to combine, let's say, index modulation with our risk technology. So again, Rohit has led this paper with us. And here we try to present a scenario where we try to get rid of some sort of successive interference cancellation unit at the receiver, because in conventional technologies, so let's say you have your NOMA or RSMA, you require some sort of decoding. In NOMA, if you want to filter out your signals, for different users and so on, depending on, let's say, power levels in power domain NOMA and so on. In RSMA, you have a, let's say, common sort of message and some private messages. You may be decoding common message at once, private for each individual user, but still you need to do some partial decoding of this interference. But we expect that maybe with the proposed framework, when you already decided the transmitter to the use of index modulation, already the combinations of either frequencies or antennas or even polarization, you may not require any interference decoding at the receiver. And we try to compare the performance as well with the conventional case of NOMA or with the conventional risk-assisted NOMA as well. And we tend to perform better with this particular framework. And again, there can be more advances as well in this. So if you want to study a bit more on how we can enhance this risk index modulation, the combination of these for different channel models or different schemes or different proposed technologies. So you can also kind of have a look through this. So I've also given a link to this paper here. We have done very recently on basically combining risk and index modulation based on spatial diversity. So basically your antenna diversity, and then how we can come up with better performance than our existing sort of benchmark schemes. But then still there are many open issues and research directions that exist in this. Is basically about the channel overhead, or how you would like to do the precoding or beamforming, and also how would you like to do this embedding of this information when you are selecting the combinations of let's say antennas or frequencies, or polarization of your antennas or of your risk metasurfaces. So these are several challenges that we need to consider when we're talking about advancing more in this direction of risk and index modulation together. So I think this would be my last topic. So I want to touch a little bit on each and every sort of research work that I do. So this is one of the last ones. Again, it is related to the 6G framework. So we had talked about multifunctional 6G framework using, ISAC, integrated sensing and communication. We had talked about to make it more adaptable. So which was the case with ubiquitous intelligence as one of the objectives mentioned in 6G framework. So smart radio environment or ESIT, these are expected that in next releases or next standard activities, we may consider these technologies. So risk at the moment is not existing in any of the standards, right? So release 18 or 19, risk does not really is a part of any of the standards, but there are non-controlled repeaters or similar sort of principle-based technologies are there included in the latest releases, right? But we do expect that with the expansion of the technology further, so it doesn't have to be just the reconfigurable intelligence surfaces, but let's say next generation MIMO, let's say using holographic MIMO or curvature MIMO or curved sort of spherical wave sort of different antenna designs, or these may make a part of the future releases or be available for let's say 6G and beyond services. But again, we do not know at this particular point what will be really included in the standards for the future and what will not be. But one thing for sure is that we have the concept of non-terrestrial networks that's definitely included since release 17. So this has been around us for a very long time. So it was discussed, let's say, even in sort of 90s as well, to consider sort of non-terrestrial entities for let's say early generations of wireless communications. Up. But in very recent years, so this has become a quite important part of our 6G sort of services, or upcoming sort of services or applications and so on. So here the idea is that we would like to use our non-terrestrial entities. So what are these non-terrestrial entities? They can be your unmanned aerial vehicles, so anything in the air, like let's say flying platforms, hot air balloons, and so on, right? Tethered balloons, right? They have different categories as well. So you have, let's say, if you are quite close to the ground, you have a low altitude flying platform, or you have like a medium altitude. And if you are a bit further away in the skies, you have a HAPS, right? High altitude platform as well. And then again, we are considering satellites as well. So basically, LEO satellites is being considered as one of the potential candidates to be used to have direct access to our smartphone through the satellite signaling. Compared to let's say GEOs and MEOs, because they are a bit far away, so you can expect some sort of latency or maybe more power push, or maybe more complexities associated if you move much forward. They have their inner communication. So when you talk about mega constellation NTNs and so on, they have their inner communication going on. So you are trying to incorporate LEOs with GEOs, GEOs with MEOs, and so on. So you do have some different technologies that have been put through. But again, I mean, for integrating our non-terrestrial entities with our terrestrial network, our current infrastructure, this is a bit of a challenge. So we want to consider what is much more feasible in next couple of years. So there have been some sort of real world scenarios or real world sort of applications that we have seen across us. So FCC in the US as well has proposed some sort of framework where satellites communicate directly with the smartphones that we have. Until now, we had been using, let's say for Apple, they had used emergency SOS services using satellite signaling. So they have Globalstar satellites, LEO satellites, 24 of them. So they use that for these services. Qualcomm also had done on the Android side, let's say, using Iridium satellites. Then T-Mobile and SpaceX had also aimed to provide 100% coverage for the US, especially for the remote places. Huawei's Mate was also one of the examples that had used this emergency SOS functioning. Motorola as well in 2023. And there have been many other sort of applications we see that how this technology is getting mature. So again, this point is a bit debatable in a way that some may say that we are advancing with fast pace, but some may say that we are still at very initial applications, SOS services. We're just trying to use, make use of one or two satellites to have this direct sort of connectivity. But again, has been going on. The work has been going on. Several industry partners have to get on board, and also there has to be some sort of spectrum harmonization as well. So basically, how you can harmonize the current cellular services that you have. That you use some frequencies, right? Sub 66 gigahertz frequencies that we use. So how can we actually harmonize these with for our non-terrestrial based connectivity as so important. And again, let's say if you talk about one satellite has coverage over, wide coverage over different regions. So how different regions can also cooperate together to provide, the unconnected, the connected sort of services. So this is also one of the most important points that we need to think that how regional regulators or spectrum regulators are going to, cooperate as well to provide services which are available to the users without any hiccups and so on. So this is quite important. Again, we discuss all these points in some of our podcasts here. So if again, I would like to pitch in here some of our podcast videos that we have done in recent months. So basically, we discuss about the future of non-terrestrial networks and what we are expecting, what are the trends and challenges that have been going on. We also take into account, let's say, different multiple access approaches to manage the interference. So we do discuss about briefly about these approaches as well. And again, we have shot a very recent podcast with one of our colleagues. So basically, there we mentioned about what has been the updates in standards related to NTN. And what kind of future trends that we are seeing for NTN technology. And I do not know how much time I have, so I would just like to wrap up quick, is that basically when we talk about NTN technology, again, picking up from 6G framework, can we incorporate AI as well with our NTN technology? So we had done one paper very recently where we tried to provide some sort of training model, deep reinforcement learning based model to enable edge cloud computing for satellite based communication services. And again, this can be used in different other sort of use cases or usage scenarios. Is basically you can use in public safety as well. So let's say if you have a drone that you can sort of if there is a sent to relay the local link between the base station that was actually serving that particular region. You can send in your drones as sort of flying base stations or just as the relayers. So basically go there to relay the information, pass it back to the base station you have. And again, you can make it more automated as well by using some sort of AI techniques, which we actually show in this particular paper as well, and make it energy efficient as well at the same time. And again, we need to keep in mind that if we are sending one drone or one, let's say UAV as well, so it may not be quite sustainable solution because they have limited battery capabilities. So we need to also find the solutions. Either we send some backup UAVs, so we send a lot of UAVs as a sort of swarm UAV sort of application, or we try to enhance this battery performance. So some sort of using free space optics or some other sort of techniques. We also try to have this longer life of the battery as well for our non-terrestrial entity. Again, there is no free lunch. So always, if you would like to have more advanced sort of applications out of these non-terrestrial entities or your, let's say, LU satellites and so on, they require high complexity or high power consumption as well. If you would like to have much more sort of services based on your non-terrestrial entities, so this is something we need to keep in mind. Again, the intelligent meta-surface technology or RIS or any other version of this can be combined with your NTN as well, so you can equip these meta surfaces on your, let's say, drones, or you can equip these on your satellites, and they can, try to communicate with the ground user, with the ground network, or they can communicate among each other as well. So depending on what is really the application. One of these applications can be also in coverage hole discovery. So we discussed this in one of the recently accepted paper. Please feel free to go through that. Again, this is basically the continuation of the previous slide. So you can have, let's say, RIS or intelligent meta surfaces mounted on your ground network, on your, let's say, any buildings or roof of a car or any other sort of mobility sort of application or any sort of vehicular application. You can also combine this with integrated sensing and communication. So basically, instead of using just a communication signal, you can use a dual function signal as well, and multiple other sort of applications we can think of when you try to synergize the advantages of intelligent meta surfaces and non-terrestrial networks. So one of these examples was that you can, instead of using just a communication signal, you can use a sensing and communication dual function signal, basically being used, having connectivity from the satellite, but again being reflected using your intelligent meta surfaces. Either they are mounted on your satellites or they are on the ground, on the roof of a car or on the roof of a building. They're mounted there. So depending on the application, I mean, it depends. You can make use of these three technologies. You can combine these together. And one of these prime examples, which I also mentioned earlier, is public safety. So basically, all your satellites, direct connectivity to your smartphone or your mobile device, or basically even from the flying platforms, let's say your UAVs and so on, in a disaster scenario where you want to actually detect some targets, send some objects, and also at the same time you want to communicate as well, where you actually have lost any sort of communication with your terrestrial network, right, because of the disaster. So this has applications in the public safety as well. Basically, you want to use your dual function signal, you want to reflect it in your intended direction of the user or of your target or your object that you want to detect. And at the same time, you are basically using your non-terrestrial entities as well. So you're not just using your LEO satellites, you're making use of your flying platforms as well. So depending on your application, you can play around with this concept and the amalgamation of different technologies together. So one of these use cases we can think of is in public safety with these approaches. And I think with this, I hope that I have not gone overboard of my talk time. But there are some upcoming talks and tutorials as well that I'll be delivering. So if you happen to attend any of these, please feel free to get in touch or follow these. So I've also mentioned, I just realized that I've also mentioned today's talk here as well, and some other talks that I'm doing this month and in the next months as well. So basically, I'll be discussing the same sort of scenarios. So sometimes when we discuss about integrated sensing and communication, so we focus just mainly on that. If we try to present a non-terrestrial network-based tutorial, we focus more on non-terrestrial networks in more details. But the today's talk was mainly aimed to touch different technologies, even briefly, but to kind of provide an idea on our research and sort of latest trends and challenges that have been going on in these technologies. So with this, I think I would finish my talk. And again, I would like to thank you for the invitation. And if you have any questions, please feel free to ask me or send me on the email. Everything goes. I mean, if you'd like to discuss any collaborations in these topics or any queries or any questions, please feel free to ask me.
Any question from the audience side?
Rohit, let me try to. How can I unshare this? Is there? Okay, let me try. Yeah, please go ahead.
Can I ask my question, or is someone asking?
Yeah, please go ahead. Ask your question.
Okay. Thank you for a very interesting presentation, and for me, it's been an eye opener. I'm very interested in the active and passive reconfigurable intelligence surface, so active RIS. Now, my question is this: what's the difference between active RIS and then cooperative communication? And are they different?
I don't know if someone is asking and we are not able to hear.
Yeah.
I'm not sure.
His question, he is asking the difference between. Can you repeat the question again?
Yes, can you hear me? Yeah, my question is, what's the difference between the relays in cooperative communication and active RIS?
Actually, I'm not able to hear anything.
Yeah. He is asking about the difference between RIS and relays in cooperative communication.
The active RIS.
Yeah, I think this is
Archive
a
RIS.
good. Yeah, this is a good question. I mean, it's often asked. So basically, so meta surfaces in general is sort of when the technology started. The idea was to basically provide more adaptability to the signaling that we have. So using different meta surfaces and different unit cells between these, you wanted to provide sort of dynamic propagation, right? So basically using different unit cells to kind of propagate your signal. Again, we do not know exactly that if it has like very big advantages over the existing, let's say, repeaters or relayers and so on. But with the advancement in risk technology, let's say through using maybe holographic MIMO or let's say some other active rays or stacked meta surface or something. So we do see that if we play around with the meta material or the meta surfaces, we do come up with some advanced sort of applications as well. So that's what I can think, that basically there is a difference in terms of that you can achieve high degrees of freedom, basically depending on how you want to make it adaptable to the changes in your environment, basically the name smart radio environment. That's why. But at the same time, you want to also have the high, more advanced sort of techniques that you can use using these meta surfaces. So the existing infrastructure is just basically based on, let's say, the repeaters or the relayers and so on. But this meta surface can provide you some additional sort of technology. I don't know if it answers the question exactly, but I do see one more question from someone. Rohit, maybe I don't know if you can read.
Yeah, I can. Okay, so we have a next question. Thank you for such an inspiring talk. My question is, in ISAC, the target echo, for example, the reflected signal is very weak as compared to the other signals. How do we process it? So the communication and radar signal transmitted at the same power level or at different power level?
So this one, I think it really depends on how you want to tune in your two operations. So basically, if you want to enhance the performance, let's say for your communication signal or the radar component of the signal, so you need to use some extra circuitry or extra, let's say in this case, when you mentioned about the target echo, about the reflected signal, so you may require some sort of technology or some sort of amplification assisted circuitry to enable this. So my point of saying here is that it really depends on tuning in which operation you want to perform better, which operation you want to give higher power level to. So it really depends on sort of this trade-off. So it is a joint system, but it depends on how you want to tune in additional circuitry or extra power or extra any other sort of technique that you want to implement for both the operations. So this is flexible, I would say, for a joint system, but it really depends on how you will design it. So let's say some radar sensing would work just on short range sort of sensing, but communication may be a bit more long range, right, at some particular frequency. But then you may need to do some changes in your system to actually enable a good operation for both the functions. So that's what I would say, that it really depends on how you want to tune in both the operations together. So there's always a bit of trade-off between ISAC operations. Yeah. I don't know if I still answered the question, but that was my thought. Yeah.
Yeah. Any more question from the audience side? So participants are requested to remain connected. Next section is going to be start as soon as we complete this. Dr. Nishant has already been connected. So meanwhile, we can answer. We can ask. We can have more questions if you have any.
Yeah.
Okay. Thank you. What about antenna? We have some connected questions, sir. Thanks.
Yeah.
And what about antennas? We have different antennas for communication and radar.
Yeah. So this again, I mean, is something that's what is your really application? So if you are using sort of coexistence, right? You may use different sort of antenna. So think in a way that this is what is done conventionally. But when we are talking about a joint system, we may use the same antenna, same metasurface, same thing as well. But your signal is a dual function signal, as I mentioned. It has properties of both the radar and communication. So when even you are designing your problem, let's say, so you're considering a joint problem, a joint mutual information problem. You consider in that one your communication part, you consider your sensing part, right? When you're transmitting, basically you consider the channel component of your sensor, channel component of your communication as well, right? But you're trying to make use of the same hardware, so same antenna, same RF chain, same everything, but you're trying to use a dual function signal. So this is a bit of shift from how we were doing our conventional sensing or conventional radar sensing or conventional communication. So in that scenario, yes, if you're coexisting them under one network, so let's say within one distance, you have your communication separately, communication units, you have your radar sensor unit separately. They are just under one network. They are trying to coexist with each other, but that is not a dual functional signaling scenario. So we are moving more towards a dual functioning signal scenario where you have a bit more, let's say, freedom to design the system in a way that is beneficial for both sensing and communication, right? You can use the same antennas, you can use the same meta surfaces, so that's the idea. You are using a dual functional signal. It has, let's say, two beamforms or two steered beams, but basically one of these contains the sensing information, one of these contains the communication information, right? So this is the same signal. It's a dual function signal. It has components of both. You can use the same hardware to be able to transmit your signal that can be sent to your targets, that can be sent to your users as well. So this is a bit different from conventional methods that we have been using. So we need to get used to this sort of technology. And again, many other sort of updates can come if you think about the technology in future years. But at this particular point, we are aiming towards using the same hardware, using the same frequency resources, so assigning one single frequency for these both these operations. I hope it answers your question. Yeah.
Yeah, we have one more request, sir, to have a small insight on the limitations of passive IRS, particularly in geo-satellite communication. Limitations of passive IRS in the purview of geo-satellite communication.
In geo-satellites, yeah. So for the passive risk, I mean, this is quite obvious because let's say when you are considering passive risk, so basically it's just a passive element, right? It does not do any amplification. And GEOs are quite far away from the Earth's surface, right? That explains the delay, the latency, and so on. So if you try to, let's say, enable communication between GEOs and LEOs, that may be a bit easier distance may not be that hard to cover. But again, this is something, it's a bit difficult. Theoretically, it may look feasible. But in a case when you want to communicate with your ground network, so if your passive risk surface is on ground network, or either it is equipped on one of the geo satellites, there is, amplification is not there, right? So you may require many of these meta surfaces. Either, let's say, you are connected first with a geo satellite, it connected with the LEO satellite, it's connected with another flying platform or something, and then it is connected, let's say, with your ground network. So the problem here is that your passive risk is not really amplifying anything. So the range may not be that bigger for your application. It may not work in a sense, because geo satellites are quite far, let's say, from the Earth's surface. So it may be difficult to just use passive risk, and also in small quantities, so to speak. So that is basically the disadvantage. Its own definition is, okay, you're saving a lot of energy. You don't require other sort of power circuitry or so on. Any amplifier, you do not require any RF chains and so on. They are passive in nature, but you're not achieving any amplification using this. So this is one of the biggest disadvantages, I would say, and especially in the case of GEO, because it's quite far away, and there is already latency problems. Already you need to push your signal a bit more, because you need to have some additional sort of power, even on the GEO satellite, to already the original signal, already the signal that is being transmitted through your GEO units. It is already difficult, and if you want to plug in even meta surfaces and passive in nature, it still stays difficult, because there is no amplification that you have. You are just doing the reflection of your signal. Yeah.
Yeah, I think you have answered all the questions. No more questions in the room. And also, I request you to participants to look at the possibilities of working with him. If you have a good plan, you can always look at his profile. You can connect him. He's very responsive. I can personally say this.
Yeah. So Rohit and I have been working, quite actively in recent years. So we have done several papers. So many of these figures and these you see, these are from Rohit. So all the credit goes to Rohit as well for many of let's say the papers that we have worked on.
Yeah, that's a combined work. The credit combines you as well, sir. Also, so I request all of you to, if you want to have a good plan, you have good proposal, you can connect him. So again, I want to thank you, sir. I know how much busy you are, since I am connected to you from years. So thank you for sparing this time for me, especially in this short note, sir.
Yeah, no problem. Thanks a lot, Rohit. And thank you so much, everyone, for attending and listening to my talk, and also putting up your questions. It was a real delight.
Yeah.
And hope to see you at the point. Yeah.
Yes, sir. It was informative, interesting, and intellectual as well. Thank you very much.
I mean, I try to keep it a bit bird's eye view sort of thing, not go into too much technical details, but whatever. Thank you.
Yeah. Thank you very much, sir.
Thanks a lot. Thank you. Take care, everyone. Bye-bye. Take care.
Bye. Okay, so next we have Dr. Nishant in the room. So